So this week, what we're going to talk about is the evidence that shows us that the Earth's surface is made up of plates that move and interact. So, evidence for plate tectonics. Last week, we talked about what the inside of the Earth looked like. One of the key things that you should bring back from that will be what a plate is. When we talk about plates, plates are lithospheres, so you can go back and review that. But what we're going to do today, or with this slide presentation, is talk about the evidence. What lets us know that the Earth's surface is made of plates that move and interact. So this is our slide defining what we mean when we say plate tectonics. Plates are rigid lithosphere. Most activity that we see is at the margins of the plates, and the plates are the surface of the Earth. So if you go outside right now and stand on the ground, you are standing on the North American plate. There are places where you can go and put a foot on the North American plate and a foot on the European plate. You can do that in Iceland. If you go to California, there are places where you can put a foot on the North American plate and a foot on the Pacific plate. So some slivers of Western California are part of the Pacific plate. But a plate is the Earth's surface, and it is lithosphere. So where did this idea come from? Well, there's a bit of a history lesson here, and it involves the history of the science of geology and people looking at the surface of the Earth and thinking about how do mountain ranges form? How do ocean basins form? Where do these features come from? Why does the Earth's surface look the way that it does? And in the really the late 1800s, when we got really good maps of the surface of the Earth and the continents, people noticed that South America looked like it fit into Africa. And when they looked across the Atlantic Ocean, you can see it looks like North America kind of snuggles up in there as well. And there were a group of geologists and people who study the Earth who said, you know what, we think things fit together. And so they did a lot of work, and the figures that I'm going to show you, the black and white ones, come from a book called Our Wandering Continents, which was published in the 1930s by a gentleman named Alexander du Toit, and he was part of a group. Your textbook talks a lot about Alfred Wegener, who was kind of the leader of that group before he passed away. But that book, Our Wandering Continents, is a really good summary of the evidence that they had at the time in the 1930s. And I think the drawings are simple and pretty easy to understand. So this is their picture showing the fit of the continents. And this is their idea of kind of what happened with the continents moving from that picture at the top where everything fits together to their present day positions. So what did they use to support that idea? Well, if you put together a jigsaw puzzle, you definitely use the shape of the pieces, but you also use the picture that is on that puzzle to determine whether or not the pieces actually belong together. And so what these scientists did was they looked around for a geologic picture on this puzzle. If you put these continents together, do you get a picture that makes sense from a geologic standpoint? And the answer was yes, and we're going to look at a few of those examples from the book, and they have some examples in your textbook as well. So one of the examples would be glacial deposits. There are a number of glacial deposits that date back to the same time period that indicate ice covering parts of South America, Africa, India, Madagascar, and Australia. And that wouldn't make a lot of sense with the continents in their present position. The ice sheet would have had to have been very large. It would have had to cover extensive portions of several ocean basins, and geologically that doesn't make sense, especially considering rocks from the same time on other continents don't show any evidence of glaciation. And if you can imagine a glacier that extends from Antarctica all the way up to India, would actually have to cross the equator. So that just doesn't make a lot of geologic sense. But as a picture on our puzzle, it does make sense. If we move everything down to a cluster around the South Pole, you can see we've got South America and Africa together here. There's India, there's Antarctica, there's Australia. They kind of cluster around. Then the picture with the edge of the ice as this dotted line does make a lot of sense. And you can see even some of the deposits that indicate the direction of movement of the ice make sense in this context as well. So those glacial deposits are an important picture on this puzzle. This diagram is a little more confusing, probably a little harder for you to understand. There's a similar drawing in the book that's in color. The key takeaway from this is, to a geologist, this is showing how we match up some different rock types across these continents. This is what we would call a correlation drawing. And you can see that things in Argentina match up with things in Cape, which is the southern tip of Africa, and Madagascar and Tasmania. So they've got some deposits going across there and then into Australia over here. And that's what this diagram is showing. And it makes sense to a geologist, may not make sense to a student new to the study, but this is actually a pretty important document because it just shows that they're going from one continent to the next and showing how some of these deposits can match up. And this shows some of their comparisons going back and forth across what is now the Atlantic Ocean here in the middle between southern Africa and southern South America. And these little lines are just connecting up features that are similar on those two continents. So this is just showing you kind of more of the detailed geologic picture. We can step back and look at some larger structural features. Before the last exam, we talked a little bit about folding and faulting and that kind of thing. A geosyncline is a large type of a fold feature, and this shows that type of structure going across South America, Africa, and into Australia. Here's one from the northern hemisphere. It shows these two ancient mountain ranges. You are probably familiar with the Appalachians here in North America. There is a mountain range of the same age in Northern Europe. It extends from Scotland and Great Britain up into the Scandinavian peninsula. If you bring the continents together, if you close up this part of the Atlantic Ocean, it makes a giant structural feature that goes right across that boundary. And so again, we're looking for a picture that we can see that makes sense, geologically speaking, if we match the continents to each other. This shows the distribution of fossil plants. So different symbols are showing you different types of fossils. So Pachypterus flora is a type of plant with a leaf, and you can see that that plant range is right around here and actually goes across into Asia. So that's India, Africa, this is Europe right here, and North America. Then down in the southern part of the world, we have a couple of other types of fossils. Glossopteris is one that shows up in a lot of the literature. That's the little bullseye pattern. And the little crosshair pattern is a different kind of plant. So you can see that these plants match up nicely across what would now be kind of widespread oceans if you bring the continents together based on shape. So again, more of a picture on our puzzle. In your book, they have this nice color picture showing you some animal fossils, and these are just two examples of animal fossils. There are more. you can see this guy, this critter is in India and Australia. This particular critter is in Africa and South America. It would be difficult for these land-based animals to swim across a wide ocean, but for them to walk across land, if everything's connected, makes a lot of sense. And so we can look at climate zones, which are indicated by plants and rock types. Remember earlier in the semester we talked about environments of deposition. You can actually use those to help you build up this kind of a picture. And then the other place that they looked, and this is where kind of the mystery was in the 1930s, was what's going on in the ocean. This was their picture of the Atlantic Ocean. You can see there's something called the North Atlantic Rise and the South Atlantic Rise. We now call those mid-ocean ridges, and we'll talk about those in the next set of slides probably. But this is kind of where the research went. Here are some ideas for what might be happening with the Atlantic Ocean. It shows you kind of a splitting of the continent and kind of pushing the two continents apart. And this is interesting because they had some ideas about what might be going on between the continents, but they just weren't sure. They were very confident in the fit in the picture. The stuff shown on these slides is where they were asking a lot of questions. And this is where the research turned after a break. The break was World War II, and World War II kind of stopped all the research. However, a lot of data was collected. So you can see these drawings here are speculative, I think would be a good way to put it. There's not a lot of detail in this picture about what's happening in the middle of the Atlantic Ocean, so there's a big question mark. And what happened during World War II is there was submarine warfare. So the Allied Navy, the United States Navy especially, used magnetometers and sonar to look for submarines. And the data that the sonar and the magnetometers collected turned out to be key to understanding exactly what was going on with the plates. So how do you get South America and Africa, North America and Africa and Europe to move apart? How do you open up the Atlantic Ocean basin if this idea that they called at the time continental drift is truly what is going on? How do you move large continents that great distance? And so we'll kind of leave our discussion off there, and we'll pick it up in the next set of slides with what happens with that data that's collected during and then after World War II, but especially during World War II. And in particular, there were some researchers who had been in the Navy and were familiar with the data that was collected and were able to go back and get that data. And you can see this picture of the shape of the Atlantic Ocean floor is much more detailed than the one that they had in the 1930s. So here's the picture from the 1930s, and here is the picture from the 1950s. And so with that greater detail, we can have a much better idea of what's going on with the movement of the continents. So I will leave it at that and tease you to watch the next presentation as well to see where this goes.